All right, the question reads, a ball is thrown from a point P with an initial velocity u of 12 meters per second at 50 degrees for the horizontal, as illustrated in figure 2.1. The ball reaches maximum height at Q. Air resistance is negligible. So, you know, the force of drag, that would be the force that sort of air exerts on an object. We're neglecting, right? So that's just negligible for this one. A, calculate the horizontal component of U. And then part two, the vertical component of U. So if the learning objective is students will explain projectile motion in terms of horizontal and vertical components of motion, you can see how this question very neatly aligns with that learning outcome. Taking the time to master that learning objective, this assessment will assess, you know, your mastery of that. So take a moment to try to answer parts 1 and 2 for question 2A for this paper. And we'll compare notes in just a moment. If you're watching this on YouTube, pause the video right now. Try your hand at the calculation, and then hit play whenever you're ready. Does anybody have the horizontal component of motion? I heard somebody say 7.7. Very good. How did you get that? Well, because the horizontal component is adjacent to this angle 50 degrees, then the cosine function is really helpful here. So we can say the cosine of our angle 50 degrees is equal to the side adjacent to the angle. So we'll call that the x component of u over the hypotenuse, which is my 12 meter per second velocity vector. So because I've already substituted in a value for theta, why not substitute in the hypotenuse too? And then it's clear to see that we can arrive at this answer of 7.7 by multiplying both sides of this by 12 meters per second. So the x component of u is calculated as the cosine of 50 degrees times 12 meters per second. And that should give you 7.7. Let's just double check that. Any questions about that? So if the horizontal component of velocity is adjacent to the angle, the vertical component is opposite that angle. And so the sine function is helpful with that. So we can think about it as the sine of 50 degrees is equal to the opposite, so the y component of u, the vertical component of u, over the hypotenuse 12 meters per second. Again, multiplying both sides by 12 meters per second, we can see that the y component, or the vertical component of the velocity u, is equal to the sine of 50 degrees times 12 meters per second. .19 or 9.2 meters per second. The question goes on to read, show that the maximum height reached by the ball is 4.3 meters. Show that the maximum height reached by the ball is 4.3 meters. If we have the equation h equals 1/2 gt squared, this is an equation that relates the height of something falling in a gravity field to the time that it's going to take. Right? So the height goes as the time squared. If we know how long it takes the object to fall from this point, which is the same amount of time it took the object to sort of reach that point, then that would be the time that we need. We know that the acceleration is due to gravity here on Earth, 9.81, and so that's what we need to solve for the height. So that's one way to go about solving for it. Does anybody know how to calculate the time to max height? Yeah, call it out. Correct. The reason why we can just take the y component of velocity and divide it by the acceleration due to gravity, 9.81, that's sort of computationally how it works, like an algorithm that you could remember. Let's remind ourselves sort of why that works. So we're applying this equation of motion at this point right here. And everything that we're sort of thinking about is happening in the y direction. So the velocity in the y direction, the initial velocity in the y direction, the acceleration in the y direction. And that's really the key idea that belongs with this learning objective. Students will explain projectile motion in terms of horizontal and vertical components of motion. Only the vertical component is accelerated by gravity. Third question?
Yeah, you just like quickly explain them. I'm kind of lost on this time. Quickly explain to me what we're supposed to do.
You mean going back here to calculate the horizontal and vertical components? So to calculate the horizontal and vertical components, we're using our trig definitions, right? So we're saying if we're launching something at 12 meters per second this way, then some of that motion is in the horizontal direction and some of the motion is in the vertical direction. We have to resolve the vector to figure out like how much of each, right? Because it's launched at an angle. So this is the same thing that we had been doing when we resolve vectors. We have a vector that's sort of pointing in a direction that's not perfectly aligned to the x or y axes, and we're resolving it. To resolve a vector is to figure out how much, of the vector acts in the horizontal direction, how much acts in the vertical direction. The reason why we have to do that with projectiles is because we apply these equations of motion, of uniformly accelerated motion, only in the vertical direction in which gravity acts. So right now we're trying to figure out how high up this ball is going to reach, right? Saying show that the maximum height is 4.3 meters. We should recognize the height as a displacement. Okay, it's a change in position. It's a vertical change in position. And so this was an equation that comes from the more general equation of motion, S equals ut plus 1/2 at squared, where the initial velocity is 0. So that term goes away. The displacement is vertical, so we call it height. And then 1/2 at squared is 1/2 gt squared because the acceleration is that specific acceleration due to gravity. So here we're just sort of applying the equations of motion that we derived from a velocity time graph. If you have questions about that, click on the link there and then watch the video where I derive those equations of motion. Students that are listening to this in class right now obviously don't have the opportunity to do that, but just go on YouTube later and it'll all be up there. Yeah. This one right here. S equals ut plus 1/2 at squared. And that's, I think, what we called equation 2, which, again, should probably be on another page of your notebook if you have that already now. All right, so we can figure out the time here, as was mentioned earlier, by taking the vertical component of velocity and dividing by 9.81. Let's see sort of why that's true. So this is one of the equations of motion that we derive. It comes from the definition of acceleration. At the top of an object's flight, it reaches a temporary final velocity of 0. Right? Gravity slows it down to a stop before it turns it around. That's equal to the initial velocity in the y direction, that 9.2 meters per second we calculated earlier. The acceleration due to gravity opposes it. So if we launch at positive 9.2, then gravity is acting negative relative to it, negative 9.81 times t. So this is just substituting in sort of what we know at this point into this equation. V equals u plus at, that first equation of motion. This is just the second equation of motion. I've got the big 4 equations of motion we're sort of using here because gravity is a constant accelerator, so we're allowed to use 0 is the velocity in the y direction at that point. U sub y is the initial y component of velocity that we calculated here. The acceleration due to gravity is sort of known, and we can solve for time. If we subtract 9.2 from both sides, we'll get negative 9.2 equals negative 9.81 t, and then we can divide each side by negative 9.81 to isolate the variable t. And indeed, computationally, it's just like whatever that number is divided by the acceleration due to gravity, that's the time to max height. So we can kind of think about it as 9.2 over 9.81 gives us the time to get to this point Q. It's the same amount of time it takes the object to fall from that point or to fall this way. Again, gravity doesn't care if you're moving sideways. Like the reason this thing still keeps moving sideways is because it maintains this constant x component of velocity. Yes?
Where did you get 9.2?
That's the acceleration due to gravity here on planet Earth.
Oh, okay. All right.
It's the result of our lab work from last week. So it's like the conclusion that we reached when we did the pendulum lab. It's also some of the data that's sort of provided to you as you sit for the papers in case you forget. So that's just the acceleration due to gravity. Okay. Even though they don't say that this is happening here on Earth, unless they tell you otherwise, you can assume that these physics problems, are occurring here on Earth, where we know the acceleration due to gravity is 9.81. So the time it's going to take to reach max height is 0.9378 thereabouts seconds. And if we want to show that the height of the ball is 4.3 meters of height, then we can just substitute that time into this equation. It's like saying it would take something this long to fall from that height in an acceleration due to gravity of 9.81. So we'll substitute here. Height equals 1/2 9.81. The units are meters per second squared, and then the time that we calculated 0.9378 seconds, that quantity is also squared. So when we square these seconds, it's going to cancel out these units, seconds squared, and we'll be left with meters of height. And hopefully it's close to 4.3 when you type that in your calculator. Give you a second to do that. So that's 0.9378 squared times 9.81 times 1/2. And we calculate the height to be 4.31, which is indeed about 4.3 meters. So it checks out. There are other ways to get to that answer besides the way that I've just shown you now. You could use a different equation of motion besides the one that we used here. As long as it includes a displacement vector, right? And you can sort of extract the other relevant information. The final thing we're doing with this is determine the magnitude of the displacement PQ. Determine the magnitude of the displacement PQ. So the displacement PQ is the straight line sort of distance from point P up to point Q. Okay, it's that sort of quantity right there. It's not the path that the ball takes, it's just the net change in position from P to Q. Does anybody have an idea about how we might go about solving it? Just like when we have this like hypotenuse here, and we said, oh, we can resolve it. We can figure out the horizontal and vertical components by using our trig definition. We could think about this displacement vector from P to Q as being the hypotenuse of a right triangle. So let's construct some legs here. We want to know this distance. And if we know these distances, these displacements, then we're good because we can use Pythagoras' theorem. Does anybody know what this displacement is from the ground up to point Q? What value of displacement is that? Correct, 4.3 meters. We just calculated, whoever said it. 4.3 meters, right? That's what we spent all this time here calculating the height, right? From the ground up to Q, right? We're drawing a triangle. Now, how will we get this value here? Does anybody have an equation in mind? I heard somebody say range equals VXT. Very good, whoever you are. So we can always calculate the range of something, the horizontal distance, okay, if we know the x component of velocity, which we conveniently calculated earlier, and the time that it takes to get there. So we had done a calculation like last week where we said, hey, once we know the time to max height, double it to get the total time airborne, and then that total time times Vx gives us the range, the total range of the projectile. Here, we're only halfway downrange, right? Like this thing will keep going. So rather than doubling the time, like we've already got the time to get to that horizontal distance. Okay, we calculated it here. So this equation works everywhere. In other words, a question could be, what is the range 1 second into the motion, which would actually be like here, because this is 0.937 seconds, like half a second, 0.75 seconds, 1 second. So we can plug in any time t and solve for where it's going to be horizontally using this equation. We want to know how far downrange it is right when it's at the top of its flight. We want to know the horizontal displacement when it's here. because then we'll kind of know everything we need to know to answer this question. I don't know why we need to know the straight line distance from P to Q, but they're asking us to calculate it. So the range here is going to be the x component of velocity, which we previously calculated, times the time, which we've also previously calculated. So meters per second times seconds will cancel out, will give us meters. And we've got 7.7 times 0.9378 to give us 7.22 meters. It's important that we don't, go and write the answer 7.22 meters down right here, because remember, that was just sort of a necessary calculation along the way. It wasn't the final answer of what we're trying to solve, which is this vector here, right? The displacement from P to Q. 7.22 squared plus 4.3 squared will equal this displacement PQ squared. So we take the square root of it, we've solved it. So this is just sort of Pythagoras' theorem, right? A squared plus B squared equals C squared. So take the square root of, the sum of these sides squared to solve it. Here I've got that value still in my calculator. Squared plus 4.3 squared gives me that. And then take the square root to get the final answer, 8.4 meters. Which, maybe I could squeeze on. Right. Final answer, 8.4 meters. This comes from ACE Physics Syllabus Code 9702, paper 21 from May, June 2016. This is question number 2.